And at this point, I'm not sure for those of you who are active thinker, I wonder if you find any similarity of this particular design to something that we talked about previously. I can give you a little bit hints. We talked about this about 2 weeks ago when we talk about a design without inheritance. Let me just get to the disadvantage for this one here, and then I'll review, I will point to you that particular design that we spoke about previously, also for connection. Okay, so now the question is, how similar are the code structure? For example, so the answer is the code structure will be very similar, even though the functionalities individually will be different. Okay, so let's just show one. The actions of all such state dependence features, display, answer, correct messages, etc. They must explicitly discriminate on the input state arguments. So remember, the input is simply the current states. So we want to say, depending on what the current state is. For example, if the current state is state number 1, we do something. Else if the current state is number 2, we do something else, and etc. And we have to follow the similar control structure for every subroutine over here, for display, for re-answer, for rechoice, and etc. Okay, let's just see one example over here. Let's say we try to display subroutine, and we got a current state over here, and then we have the conceivable precondition over here, right? Depending on how many states you have. So now, how should we write this code over here for display? Well, you want to say something like, if the current state is equal to 1, I'm going to display something related to the initial panel. If the current state is equal to 2, I'm going to display something related to the second state. According to the finite state machine, you can look it up yourself. It's to do with the flight inquiry panel, and etc. Okay, and then we need to write. You can say, finally, if all the previous 5 did not satisfy, then I can display the final panel, right? So now, depending on how many states you have, it determines the size of the if-else-if branches you're going to have. Okay. So now here's the question: why such design smells? That's the question. Right. So now, before you can answer me this question here, you know the answer already. We have already exposed you to such design previously. So let me just switch back to my iPad, and let me give you some reminder over here. So let me just go to that particular slide previously. I believe it is this one here. Does this ring the bell to you? So this is the design that we spoke about when we talked about the student management system about 2 weeks ago. And then this particular design attempt, what we're doing is we say for every students, right? So we kind of collapse all kinds of students into a single class. And the way we can distinguish between different kinds of students is by the kind attributes, which can be 1 or 2 or 3 or 4 and etc. Right? So now, why is this design bad? Right? We spoke about it might violate cohesion, so I'm not going to repeat that part. But now, specifically, why would this particular design violate single choice principle? So that's something I would like you to recall. Okay, I'm going to briefly summarize our results from the previous week, but in case you still got doubts, you may want to review just this part of the lecture in detail from the recording. So the reason that we're going to violate the single choice principle for this particular design is because for every routine that you're going to define, you have to discriminate on the value for the kind. Over here, you want to say if the kind is equal to 1, you do something. If the kind is equal to 2, you do something else, and etc. But for another routine, you can see register has nothing to do with get tuition. However, both of them need to discriminate on the value of kind to know what kind of student they're dealing with, so they can act accordingly. You can see we have to repeat the structure over here. If kind is equal to 1, I do something. Else if kind is equal to 2, I do something. So it's exactly orange highlight over here that we are repeating. And then we spoke about if there's one more kind that's added, or if there's one kind that becomes obsolete, how we're going to violate the single choice principle, right? That's what we spoke about previously. I'm going to let you review that part of the lecture and then try to draw a connection from this design scenario to what we are talking about for execute states. So they are really relevant to each other. So I would like you to draw that connection here. So this kind of design flaw actually occurs quite often. So many people, even though they're really programming in an OO language, but if they try to program in this way, it's as if they're using a purely procedural language like C. So in that case, you're really wasting the OO ability given to you. So that's the point I like to make very strongly. Okay, let me now go back to the particular page that we're talking about, which is the display over here. Let me just go back here. Okay, so now we want to know why this design is bad. Well, the answer is the same reason for the poor design that we talked about previously. Is because it violates the single choice principle. Because for every subroutine at this level over here, display, read, correct, message, and process. For each one of them, we need to repeat the following control structure. We have to say if the current state is equal to 1, and also else if the current state is equal to 2, and also else. So the orange part will be repeated over this, and this. So that's why it's violating the single choice principle. Let's see some scenarios of extension to really convince you. Okay, let's go back to the slides. Because the same list of conditional repeats for all the state-dependent features, right? I already talked about it. So now let's see some possible changes. Why it violates single choice principle. So now, for example, if you want to add or delete a state, for example, right? So now let's say this. So currently we only got state number 1, 2, and all the way to 6. What if we want to add a new states? Let's say we want to introduce a new states. In that case, what should we change? Well, let's say for the display. So now let's say we used to get only up to 6, but now we're going to get maybe 7. Let's say we want to introduce state number 7 as well. Well, in that case, what you should do is you should really introduce maybe another, I would say, else if over here. You might say else if over here the current state is equal to maybe 7. And then you're going to do something over here. But is that the only place you have to change? Well, not really, because this is only for the display. And at the same level, you got other routines. You got to make a change to the read. You got to make a change to the correct. You got to make a change to message. You also got to make a change to process. So there are really multiple places you have to change by adding this particular else if statement to really discriminate on this particular new states, number 7, right? So this will definitely violate the single choice principle. So that's point number 1. Okay, proof number 1, if you would. Okay, so now another scenario will be, let's say if you delete a state, right? I just talked about adding a state. What about deleting a state? Similar. Okay, let's say, for example, if we decided that state number 1 is no longer applicable to our application. So what I would do is, rather than having 1, so let's say this starting state should be 2. So that means I'm going to delete this particular branch over here. It's no longer needed for discrimination. So I'm going to delete this. But is that the only place I need to delete? Not really. We only deleted just the display. We also need to delete for the read, for the correct, for the message, and for the process. So it's actually multiple places we will have to delete. Again, it violates the single choice principle. Okay. So also when you delete an existing states. Okay, I'll just put down the so for example, we want to delete number 1, right? That will also violate single choice principle. But you can also think about other scenario where you simply just want to make some change to your states, not necessarily just to add or delete, maybe redefine some states. In that case, you will still need to change multiple places. Thus, you're violating the single choice principle. All right, let's go back to where we were. So again, I will really strongly advise, try to look at this particular design flaw as a connected problem to what we talked about previously of having the kind attributes in the student class. We're really talking about the same kind of design flaw, but in different context. So that's something I would like to emphasize once more. Let's go back to the slides. And then, again, so this is our overall picture for the call chain, the caller-callee relationship. We got 3 levels as we just described in details. And this is exactly the passing of the data. You can see from execute session, we pass the state information, especially the current state value, to execute states. And from execute state, we also pass the current states to each of the level 3 helper routines, so it discriminates on the state value and do something accordingly, right? That's something we spoke about already. So too much data is being transmitted, especially current states being passed. So that's something we would like to avoid, really. If we can get away from to discriminate the current state value on each of the routines at level 1, in that case, we will be able to satisfy the single choice principle. That's something we would like to head to for the ultimate solution. So from the execute session to execute states, and also from execute state to all the feature. Well, exactly. That's the how the data is being transmitted. We would like to change that. We would like to improve it. Okay, so there is a law of inversion. So it's more like a design technique over here. Let me explain to you. When you read it out, formally, it may not sound very intuitive. If your routines exchange too many data, so this sentence here simply means we are really exchanging over here. We are basically changing the state information over here too much. Current states, actually this one here. You can see the current state is being exchanged from here to here, and also the current state is also being changed from level 2 to also level 1, right? So that's about too many data is being exchanged. I just want to say that. In that case, you want to put your routines in your data. Okay, so this part may not be so intuitive. What that means is the data here in our case will be a module. So now, rather than having so many routines that depend on the current states, why don't you put all those routines into a single class or a single module, so that the current class or the current state will simply just be implicit. When I say implicit, in Java, this is this keyword. In iPhone, it will be the current keyword. So that's some hints to you when we move on to the next ultimate solution in the next video. But let me finish this. Okay, for example, so now when you say execute states and all the features at level 1, right? So now so they simply just pass around the current states, and then they build upon using discriminations on the current states. So this would be something we would like to improve. We want to somehow eliminate this particular input parameter. That's something we would like to do. But if we simply eliminate the current state as the integer value, but what happened to these routines? How can they be executed? Okay, think about these are all the routines, right? Put all your routines. We're going to put all these routines over here into a single data, a single module, and the module is going to represent a single state. So that's something OO is very capable of doing. So that's something we'll see in the next video. So number 1, the ultimate solution will be we want to modularize the notion of states as a class states. Think about the state over here is the data, and then the state over here is an abstraction of the conceptual state over here, okay, the integer. So rather than simply an integer to represent the states, we want to use a class to represent the states. And all the state dependence routines over here, they will become the routines of that particular class. That's something we'll like to do. And also, we want to encapsulate the state-related information via a state interface. So interface here will definitely just consist of all the routines that depends on the states, right? So that's how we move from design attempt number 2 to the ultimate solution. Okay, so the notion of current state becomes implicit, the current class. So this line here, it will be very, very important. So later on, when you review this particular lecture, you want to really see how we make a transition from the design attempt number 2 to the ultimate state design pattern. It's really about, rather than having the current states being the integer, now we want to have the current class being the state class. So that's the main thing we would like to do. Okay, so this final slides simply summarizes what we want to do. So now what we're going to do is we're going to decompose our hierarchical design into 2 parts. One part is everything that has to do with the current states, starting from the execute states, display, read, correct, message, and process. We will put them, we'll modularize them and also encapsulate them into a single state class. That's something you will see first when you see the ultimate design. Number two, for the rest of the system, the blue part, we're going to make it just application, like a clients of the state design pattern. So we have a very, very clear separation between the clients, which is a application, and also the supplier, which is the state class. That's something you will see in the next video.